Today we're going to look at representing functions as power series. In particular, we would like to exploit some facts that we know about geometric series. So let's look at the function 1 over 1 minus x. Well, we can write that as the sum of a geometric series. It's in fact 1 plus x squared plus x cubed plus x to the fourth, etc. That is the sum from k equals 0 to infinity of x to the k. We actually solved this problem first by looking at the geometric series and then doing some algebraic manipulation to show that the limit of the sequence of partial sums was 1 over 1 minus x. But now we're going to look at this problem in reverse. We're going to think about the function 1 over 1 minus x, and we're going to use the fact that it can be written as a geometric series. And that geometric series is in fact a power series. And its coefficients for that power series are all just 1. And we know that this geometric series converges as long as the absolute value of x is less than 1. And so we can say that this function, 1 over 1 minus x, can be written as an infinite series as long as absolute value of x is less than 1. I would like you to see that graphically by looking at the graph in Desmos. So the red curve that you see is 1 over 1 minus x. And now I'm going to put in the series, and this will be the first two terms of the series, 1 plus x. And you can see that the blue line, 1 plus x, is in fact the tangent line to 1 over 1 minus x at x equals 0. And then I can add a new term, x squared, so that my series is 1 plus x squared. And that looks like a little bit better approximation of 1 over 1 minus x. I can add the x cubed term and get a better approximation. Adding x to the fourth or x to the fifth gives me a better approximation. And I can keep adding terms all the way up to, say, x to the 10th. And you can see here that the partial sum, 1 plus x squared all the way to x to the 10th, is a pretty good approximation of 1 over 1 minus x as long as I stay between minus 1 and 1. You can see that as I get closer to minus 1 and 1, that the blue curve diverges a little bit from 1 over 1 minus x. I can increase the accuracy by going up to x to the 20th, okay? And it still converges there between minus 1 and 1, but it doesn't converge to 1 over 1 minus x beyond that interval. You can see that it clearly goes away from 1 over 1 minus x as you go towards x equals minus 1. And then there's an asymptote at x equals 1. And so beyond x equals 1, of course, this polynomial is not going to converge to 1 over 1 minus x because it is in fact negative when x is bigger than 1. And so this series converges between minus 1 and 1. And a good way to think about whether a series like this a power series like this is going to converge to the function is to look at discontinuities of the function. This function is discontinuous at x equals 1. And it turns out because this function is discontinuous at x equals 1, that's exactly where this series is not going to converge at x equals 1, and then that'll define the radius of convergence between minus 1 and 1 because it cannot converge for x bigger than 1. And so discontinuities help us understand what the radius of convergence might be for a power series that converges to a particular function like this one, 1 over 1 minus x. Okay, so now what I want to do is I want to exploit this trick of writing 1 over 1 minus x as a geometric series. So in fact, let's look at 1 over 1 plus x squared. We can think about that as being 1 over 1 minus a negative x squared. And so negative x squared is performing that R role where we're looking at the sum of the geometric series as being 1 over 1 minus R. So if I want to write this as a geometric series, it would look like something like 1 plus negative x squared plus negative x squared squared plus negative x squared cubed plus negative x squared to the fourth, etc. So that looks like 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth minus, etc. We can write that as the sum from k equals 0 to infinity of essentially negative x squared to the k power. But I can simplify negative x squared to the k power. That, in fact, is negative 1 to the k, x to the 2k. And so this is indeed a power series. Its coefficients are negative 1 to the k when when k is even. And its coefficients are 0 when x is odd. But again, this power series is going to converge when the absolute value of negative x squared is less than 1, because that's r less than 1. And of course, that's the same as just saying when x is less than 1 in absolute value. So here we have another function, 1 over 1 plus x squared, and it converges. Can be represented by this power series when absolute value of x is less than 1. So now that we've kind of seen how to use geometric series to write some functions as series, we can now ask the question about are derivatives and integrals of power series convergent? Okay. What is the radius of convergence for the derivative or integral of a power series? So I want to, in particular, start by looking at this series. F of x is going to be c sub 0 plus c sub 1x plus c sub 2x squared plus c sub 3x cubed, etc. So in other words, my series f of x is going to look like the sum from k equals 0 to infinity of c sub k x to the k. And I want to know where does that series converge? Okay, I'm going to state that it converges for x less than r, but what is that going to tell me about the limit as k goes to infinity of ck plus 1 over c sub k? So let's look at what happens when I do the ratio test. I would get the limit as k goes to infinity of ck plus 1 over ck in absolute value times x to the k plus 1 over x to the k if I'm performing the ratio test. X to the k plus 1 over x to the k gives me an absolute value of x. And then times the limit as k goes to infinity of ck plus 1 over ck in absolute value. And I want that whole thing to be less than 1. So if that's the case, what must that limit be? That limit must be 1 over r. That's so that I get absolute value of x times 1 over r is less than 1, okay, or the fact that x is less than r. So when I have a power series with a radius of convergence r, then the limit of the ratio of the terms ck plus 1 over ck must be 1 over r. Okay, so now that I've shown what the limit of the ratio of the terms is, I now know that I have my function here, f of x. It's just a sum from k equals 0 to infinity, a c sub k xk. And what I want to know is, does the derivative of that series converge? So the derivative of c0 is 0. The derivative of c1x is just c1. The derivative of c2x squared is 2c2x, etc., etc. I can write this out in summation notation. I'm going to start at 1 because the derivative of c0 was 0. And so this is the sum from k equals 1 to infinity of k ck x to the k minus 1, just taking the derivative term by term. And the question is, does that series converge? Well, we can use the ratio test to see. This is the limit as k goes to infinity of k plus 1, ck plus 1, x to the k divided by k ck x to the k minus 1. Now x to the k over x to the k minus 1 gives me an absolute value of x. And I'm left with the limit as k goes to infinity of k plus 1 over k times ck plus 1 over ck. Well, the limit of k plus 1 over k is just going to be 1. And the limit of ck plus 1 over ck, well, that's going to be 1 over r. So this limit is going to be absolute value of x over r, which by the ratio test needs to be less than 1. So that tells me that this is going to converge for absolute value of x less than r. And so what we've shown is that if a power series has a radius of convergence r, then its derivative also has a radius of convergence r. And that allows us to take a power series and take the derivative of it term by term and show that it also converges with a radius of convergence r. Now, another question is, if I have this power series, f of x, which is the sum from k equals 0 to infinity of ck x to the k, can I take the antiderivative of that series term by term? Meaning if I start with c0, its antiderivative is c0x, and then c1x, its antiderivative is c1 over 2x squared. And c2x squared, its antiderivative is c2 over 3x cubed, etc., etc. If I take antiderivatives term by term, well, then I would get the antiderivative of x to the k is 1 over k plus 1 x to the k plus 1. And then the question is, does that series converge? Well, we would use the ratio test again. The limit as k goes to infinity of, here we're going to have ck plus 1 over k plus 1 times x to the k plus 1. Excuse me. Ck plus 1 over k plus 2. X to the k plus 2, and then we're going to divide that by ck over k plus 1 x to the k plus 1. So x to the k plus 2 over x to the k plus 1, that's going to give me an absolute value of x. And then I'm going to take the limit as k goes to infinity of ck plus 1 over k plus 2 times k plus 1 over ck. Now, the limit of k plus 1 over k plus 2 as k goes to infinity, that's going to be 1. And then the limit of ck plus 1 over ck, that limit is going to be 1 over r. And so this is going to again give me x over r is less than 1. And so we can say that the antiderivative also converges for x less than r. And so what we've shown is that if a power series converges for x less than r, then its derivative and antiderivative or integral also converge for absolute value of x less than r.